hello everybody. Today we are going to now discuss further on the next topic in this course on supramolecular chemistry, and today we are going to now start a discussion on stimuli driven supramolecular processes. This is a very important area of research, and there has been a lot of development which has happened in the past 1 decade when different kind of materials, particularly those which exist in the solid state, have been subjected to a different kind of stimuli. The stimuli can be of a physical nature, it can be of a chemical nature. For example, in case of chemical nature, we can expose the crystal to different kind of solvents, or we can add a new chemical entity and see whether the crystal possibly undergoes a chemical reaction with that, or we can change the pH of the medium in which the crystal has been obtained. Physical stimuli means we can actually expose it to light of a certain frequency. For example, we can expose crystals to the UV light, and it has been observed that under the presence of external stimuli, crystals also change their shape, and they also sometimes undergo different kinds of mechanical deformation because of the buildup of the stress in the crystal, and this has given rise to the area of mechanically responsive molecular crystals. We will discuss some of these as well, and stimuli can also happen by the application of stress in the crystal, where you physically apply stress on the crystal. So sometimes the mechanical strain which is developed in the crystal is a consequence of light, like say for example UV light, and you can also apply stress physically on the crystal and see how the crystal adapts to the applied stress. So stimuli can be of different types. The first case today I am going to discuss with you is a very interesting case where we have looked at crystal to crystal transition in a chemical system in the presence of silicon oil. This is a very interesting observation which we had, because most of the times we are using silicon oil to mount the crystals. So once the crystals of a particular compound have been obtained, the routine procedure is to take the crystals on silicon oil, because during the process of mounting, the crystals can actually jump, or they can fly, or they can actually go, they can be lost. So to prevent that process, we use silicon oil, and most of the time this silicon oil is an inert compound. It is non-reactive. It is something with which the crystal of interest does not interact or react. But what was surprisingly observed is when we looked at this particular set of molecules, where we have the ethynyl substituted amides, and in this regard we have looked at two particular specific isomers, one in which R1 is fluorine and R2 is hydrogen, in the other case when R2 is fluorine and R1 is hydrogen. And what has been observed, so when R1 is equal to fluorine, we call it the orthoisomer. When R2 is equal to fluorine, we call it the metaisomer. And what has been observed after a very systematic study, that the crystals, the crystals of the compound which is the orthoisomer, exist in two polymorphic forms, which we designate as form 2 and form 1. And what has been observed is that in the presence of silicon oil, which is a chemical stimuli, or in the presence of heat, that is it is a thermal stimuli, conversion from form 2 to form 1 takes place. Whereas in the metaisomer, what has been observed is that conversion from one form to another form takes place, and that takes place before melting. And now when you cool the crystal, the form 1 crystal, it does not convert into form 2, it rather converts into a new form, which is the form 1D. So, keeping in mind the fact that these crystals are very sensitive to external stimuli, namely chemical and thermal stimuli, we now look at this event more carefully as to what was actually observed under the microscope when on which the crystals were kept in silicon oil, and this is what was observed, and this is a very interesting observation, and this is the first such observation in a molecular crystal. So, to start with, we have the ortho compound and we have got the plates, as you can see here. This is the initial shape and size of the crystals. We start with the initial form 2, and what we observe is that within 15 minutes some needle like projections were seen on the surface of the plate crystals. These are the needle like projections which we see, and as the time continued, that is within a period of 1 hour, a large amount of needle like crystals had grown on the plate crystals, and after a period of 6 hours the conversion from form 2 to form 1 was complete, when the plate form had converted into the needle form. This process took place at a relatively faster rate for the orthoisomer. When we went to the meta isomer, we started with the initial set of plate like crystals. Say on a given day we started in the afternoon. On the same day, after 5 hours, we saw the appearance of this needle like crystal. Okay, now we see these crystals which are appearing the needle like. Now please keep in mind that we have got the same orientation, the same image. We are not moving the crystals on the glass slide, but we are just observing on the glass slide as a function of time what is happening to these crystals. And then after some we see that on day 2 in the morning there has been a conversion from form 2 to form 1, where you can see more growth of needle like structures. You can see these needle like projections which are coming out, and eventually the plate form has converted into a new phase. This is also indicated by the loss of transparency in the crystals. So, these crystals are normally optically transparent, but now you see they become opaque. So, when there is a phase transition from one form to another, these optically transparent crystals now become opaque, indicating that there is a conversion from one phase to another. So, the next thing was to actually now see this thing more carefully under the microscope, on which we actually now apply heat. So, we see that the stimulus here was in the presence of silicon oil. In the presence of silicon oil, we were able to achieve this transformation, and the next question was that what if we take other oils or we take other liquids, for example long chain fatty acids, the dicarboxylic acids, or we can take glycerol and other glycols, and when the crystals were put in other kind of these hydrophobic liquids, no phase conversion was observed. So, this was a very extensive screening of the crystals of this particular compound in different kind of oils, different kind of fatty acids, and different kind of glycerol, and also long chain alcohols, but no such phenomena was observed. It was only very specific to that of silicon oil. And now we also wanted to see this phase transition from form 2 to form 1, and we put the crystals under the hot stage microscope. So, here you can see that we first start with room temperature, where we have isolated separately the crystals of form 2 and form 1. You see this is a nice transparent crystal, this is an opaque one, and now at around 90 degrees centigrade you see that the form 1 starts growing. As we have already discussed in our chapter on phase transitions, that phase transitions takes place by different models, and the most popular model is the nucleation and growth model. So, this process of phase transition from one form to another takes place gradually, continuously over a period of time, and it starts from a particular region in the crystal and it essentially propagates this crystal phase propagates, and it propagates via the nucleation. That means the nucleation of the new phase start from one particular region of the crystal, and then this propagates, and eventually the entire mass of the crystal it covers, where it has transformed from one form to the other. And now you can see that it has converted into the form 1 at 93.5 degrees centigrade. This is the form 1, and it is also becomes opaque. And once it has converted from form 2 to form 1, we can see that they both melt, because this was also the form 1 crystal. The crystals melt at 102 degrees centigrade, indicating successful conversion from form 2 to form 1, followed by melting of the form 1. So with these kind of experiments, we can actually validate the nucleation and growth model as to how this phase transition took place, what are the physical changes taking place. Also, it has to be kept in mind that no solvents are included in the crystal structure of either form 2 or form 1 for both the ortho and meta isomer, and no silicon oil is also found. That means silicon oil did play a role in initiating the transformation from one form to another, but there is no inclusion of silicon oil in the final structure. Now the next thing was to actually look at the crystal structures of both these forms, and this is something which is very, very interesting, that in the presence of silicon oil or heat, as we mentioned, the form 2 converts into the form 1, and you can see the dramatic change in the crystal packing. There is a dramatic change in the crystal packing. In here, I again re-emphasize, you can see here that this forms a layered structure, where the different colors indicates the different molecules of the asymmetric unit. That means the basic unit of crystallization is actually, you have this purple and this yellow color, and now you can see the purple colored molecules they stack in this direction, and these yellow colored molecules also stack in the other direction. The separation is close to 3.8 angstrom, which is essentially the van der Waals gap, and for the violet molecules this gap is slightly reduced, 3.7 angstrom. So you have got this pi stacking which actually packs the molecules into a layered structure in the form 2, whereas in the form 1 we have now got a double sandwich herringbone structure. This is a double sandwich herringbone structure, where you can see that you have this sandwich which actually has this perpendicular arrangement, So this gives rise to the herringbone structure, and the dotted lines indicate the different intermolecular interactions which are present in this herringbone structure. As you can see here very, very clearly, that you have a CH N hydrogen bond here, you have a CH pi hydrogen bond. So you have the, and you have the CH pi. The CH pi is not only with the phenyl carbon but also with the acetylenic carbon. The ethylenic carbon also interacts because of the pi electron density. So we have these CH pi weak interactions which stabilize the final structure, and you can also see the dramatic change in the structure when it transforms from form 2 to form 1, which has been mediated by the silicon oil or the heat. Now this kind of dramatic changes in the crystal packing without loss of crystallinity is very much unprecedented in the literature, and this turned out to be a really interesting case of silicon oil induced phase transition in molecular crystals. And to summarize, we also did further studies where we actually grew the morphology of the crystal. You can actually use a software to compute the bulk morphology, and what was observed in the bulk morphology was that in the case of form 2, it is the acetylenic bonds which are actually exposed on the surface. So there is possibly an interaction of the unsaturation corresponding to the triple bond with the silicon vacant orbitals, and these interactions between a large number of these isolated or exposed triple bond with the silicon oil which is present in the vicinity of this crystal can possibly trigger a process where some of these molecules dissolve in silicon oil, but immediately it also templates the crystallization of a new phase. Again, this is only the initial process which we have speculated. The dynamics are extremely fast and it has been difficult to capture these and understand how these are triggered and what is the pathway to go from the initial phase to the final phase. So, this was one very interesting example of silicon induced transformation in crystals. And now we go to the next set of stimuli which are of interest. So, we now see that stimuli in molecular crystals can actually come in different ways. We just now looked at a case of thermal events which can trigger phase transitions in molecular crystals. We can have optical stimuli, that is the presence of light which can lead to changes in the crystals. We can have mechanical stimuli, we can have the role of humidity and also the role of pH which can be a stimuli in molecular crystals. Now, what is the response of molecular crystals? It has been observed that molecular crystals, when they are subjected to different kind of stimuli, and in this particular discussion now we will be focusing mostly on mechanical stimuli. It has been observed that the crystals can bend, or they can undergo twisting motion, or they can undergo coiling motion. So, this is very interesting. It was perceived till now that crystals actually are kind of inert objects. The molecules which are present in the crystal are kind of inert, and it is very difficult for them to respond to any kind of external stimuli. But now, with the research in the last 2 decades, it is indeed been observed that crystals are very sensitive to external stimuli, and they can undergo macroscopic changes in the shape, size, and different kinds of motion can be observed wherein there is conversion of the applied mechanical energy to different kinds of kinetic energy as we observed. So, we can have kinetic energies changes, for example, ballistic motion. We can have splitting of crystals. So, the crystals can break into different pieces, different parts or different sizes. We can have explosion of crystals. We can have shape shifting in the crystal, and then when you apply the mechanical stress, when you apply the shape shifting and when you withdraw the mechanical stress, then it comes back to the initial shape. We can have self healing of crystals. For example, if the crystal has cracked, and then when you again bring it close to each other, then the surfaces can again heal and the crystal will get back its initial arrangement where the cracks completely disappear. And these applications of dynamic crystals is of interest in the field of sensors, design of electric materials, optical waveguides, drugs, because drugs after they are prepared, they are also subjected to mechanical stress, particularly in the process of tableting or applying of the pressure to achieve compaction. So, it would be interesting to see what is the response of drug molecules, particularly the crystals, to the external stress, flexible semiconductors and actuators. And what is very important to keep in mind that when you apply mechanical stress, on the crystal, you can actually have different kind of events, and what is important is to keep in mind the stress strain relationship. So, there are different regimes, and under the application of small amount of stress, there is a strain, and this is what constitutes the Hooke's law, that stress is proportional to strain within a narrow limit. So, within the narrow limit till permanent deformation takes place. If you withdraw the stress, then it will come back to the initial configuration. And these kind of systems are called elastic crystals. Whereas, if you continue to apply stress, then it goes into a non-elastic regime, from where it does not come back to the initial configuration. Those kind of crystals are called plastic crystals. So, all plastic crystals definitely go through the elastic regime, but plastic crystals by and large, when you withdraw the stress, they do not come back to the initial configuration. So, the restoration of the shape does not take place. And what has been done is that people have now applied different stimuli for a plastic crystal to be, so that it restores back to the initial configuration. However, in the case of elastic crystals, they do get back their initial shape. So, with this thing in mind, it is of relevance that we look at the elastic to plastic regime, and sometimes we call this elastic plastic spectrum, and it is of important to modulate the crystal in a way that either you can get an elastic response or a plastic response. And what has been proposed are different structural models to achieve elastic deformation as well as plastic deformation. And so, we start with an initial arrangement of molecules in the crystal, and when we subject it to stress, which such that what happens is that the molecules in the outer arc are present in this fashion, where the separation between the molecules is gradually increasing, and here you see that there is a compressive stress here, the molecules get compressed, and here the molecules get elongated. So, you have got actually expansion followed by in the outer arc, and there is compression in the inner arc on bending. And what happens is that because when you withdraw the stress, the shape recovery takes place, it comes back to the initial configuration. So, you essentially have reversible deformation, and you have an interlocked crystal packing for shape restoration. So, what happens is that you have a crystal, and now you have different intermolecular interactions. So, these intermolecular interactions actually now allow the molecules to move only in a limited way, so that beyond a certain strain they actually lock the structure, so that the movement of molecules does not take place. So, elastic crystals essentially lock the molecules into a certain arrangement via initial displacement, such that when you release the stress, they again come back to the initial configuration. And this requires a structural buffer, essentially consisting of large amount of weak interactions, because the weak interactions can be easily broken, so they can allow movement of molecules to a certain extent. But then beyond a certain stage, there is a locking of the structure, because now there is no free space available for the molecules to move further. So, that kind of limits the extent to which the movement of molecules can take place, and also limits the extent of deformation. And so, the structural buffer is very important, and this can lead to either 1D or 2D elastic deformation. So, elastic deformation is a very interesting phenomena. On the contrary, in case of plastic model, what we have is that the interactions are weak, and they actually prevent they do not prevent slippage of molecules. There are certain planes along which you will have irreversible movement of molecules, and this will lead to permanent deformation in your crystal. So, and this mostly happens in anisotropically packed crystal, where you have got strong interactions in, say, a sheet, say a layered structure, but perpendicular to the sheet you have got very weak interactions. So, when you apply stress, you can have molecular migration of the molecules over long distances, but because the interactions between these layers is weak, but then within the layer the interactions are very strong, and that can be the basis of plastic deformation. So, let us look at these cases. And the first case I would like to present here is in this particular organic system, where these molecules have been synthesized, and where the researchers have looked at 4 different compounds, where the scaffold is fixed, and then we have got different substituents. We have got the chloro one, then the chlorobromo, then the dibromo one, and then 2 chlorine atoms on the same phenyl group. Now, what has been observed is that these are the crystal morphologies. The crystal morphologies are given here for these particular compounds, and then we do something called a 3-point bending experiment, where we actually apply stress in this region. So, we apply stress on this region and we fix this region, and this is done using a pair of forceps. We call this a 3-point bending experiment. So, you have a crystal, we bring in the forceps here, we hold this particular point here, and then we apply stress like this on the other 2 parts, and then you see that the crystal can now deform, and this is mostly done along the major faces. So, if you apply the stress on the major face, then either if the crystal is brittle, it will crack immediately, it will break into pieces, but if it is not brittle and it can adjust to the or adapt to the applied stress, it will deform, and this deformation can be either elastic if you have applied relatively less stress, but if you apply more stress, it can become plastic in nature as well. So, the idea is to do this 3-point bending experiment, and this can be done on different faces, different major faces of the crystal. And as you can see here, that this is the plastic crystal in the sense that it has, on application of the stress, it has now deformed, and this is irreversible deformation such that when you release the stress, it continues to maintain the final shape. The same thing happens for the chloro and the bromo compound, dibromo compound, and in the case of the dichloro, in this particular molecule, the extent of deformation is quite reduced, and it deforms within a limited range beyond which the crystal breaks into pieces. And the careful analysis of the crystal structures reveal the following. So, here you can see that in the chloroisomer, the chlorine, we can see that the chlorine atoms are close to each other. In this case, we can see that this is again the chlorine atoms which are close to each other. We also have these layers which are held by these CHO hydrogen bonds. So, they form a nice arrangement of molecules along the A axis. But what is interesting is that now when you apply the stress on the 001 phase, so the 001 phase is when you apply it, then you will see that there is a sliding of these molecular layers. There is a sliding of these molecular layers in this particular direction, and this is referred to as the slip plane along which the molecular migration takes place. So, it is when you apply stress on this particular phase, that is the 001 phase, then you will see that the molecular migration takes place. The molecules can move in a facile way. So, because there exists very weak halogen bonded contacts here, and so this facilitates migration or the movement of the layers in an irreversible way, thereby leading to plastic deformation. The separation actually is longer in case of the when we have the bromo chloro compound. So, here you see these are the 2 chlorine atoms, and on this side you have got the 2 bromine atoms. The separation is around 2.1 angstrom, here it is around 2 angstrom, and when we go to the corresponding dibromo case, again we can see the separation here is similar to what it was in the previous case. Here it is around 2 angstrom, and this is interesting that irrespective of whether you have chlorine or bromine, the separation between the layers is similar. So, these again facilitate the migration of molecules over long distances, leading to plastic deformation. However, in the case of the dichloro compound, as you can see here, the dichloro molecules, the dichloro atoms in this molecule kind of are present between these 2 molecules in the gap which is created. So, this kind of does not really facilitate long range migration, because after a certain displacement these molecules tend to get locked. These molecules tend to get locked, and because they tend to get locked, they do undergo some minimum amount of deformation which is seen here, but beyond that the crystals simply crack because of the brittle nature, which sets into place when you actually apply greater amount of stress. So, these features which are the supramolecular chemistry of these compounds, and looking at the packing, the layers, and then the migration of the molecules in between the layers across the slip planes, allows us to rationalize the observed plastic response which is on the application of mechanical stimuli to these crystals. So, with this I think we have discussed many cases of interesting cases of stimular responsive crystal, and now in the next lecture we will now go to more supramolecular entities which react to the presence of light, and we will look at some processes related to supramolecular photochemistry and so on and so forth. Thank you.